Let's do some examples to make sure we know how to use the lens maker's equation. So here's our lens maker's equation. 1 over the focal length is equal to the index of the material, index of refraction of the material minus 1, times the quantity of 1 over R1 minus 1 over R2. Okay, that's our lens maker's equation. So let's take a couple examples. If we choose our regular biconvex lens, okay, just looking at that lens, I know it's a converging lens, which is meant for a positive lens. Okay, so a positive focal length is the same thing as a converging lens. And so this must be positive, so F must be positive. This whole thing must be positive somehow. Okay, so remembering our same rule, where does light go? First of all, this is the first surface, okay, and its radius is over there. Okay. Now light from this object hits the lens and goes this way, so that's going to be positive. There's another surface, its radius is over here, and it's the second surface the light hits, but it's on this side, it's the same side of the object, so the light's really going over here, which means this is negative. Okay. Now, no matter what their size is, I plug that in here, I get 1 over F equals n minus 1, 1 over R1 minus 1 over a negative R2, and those minus signs cancel, and I get a positive number plus a positive number. This will always be positive. Okay? So a biconvex. So it verifies that I knew it should be positive because it's thicker in the middle than at the edges. Okay, let's do a different example. Here's one. Alright, it's called a meniscus lens. Okay, so should it be positive or negative? Should it have a positive or a negative focal point? Well, our general rule is that it's thicker in the middle than it is at the edge, just like this one was. So even though it's weird looking, this still should have a positive focal point. So let's check it out. So we're saying it's got to be positive by our qualitative convention. Our object's over here, light's going here, so we know this is the positive area, that's the negative area. Well, we have this shallower curve has a bigger radius because it's almost flat, and that's the second surface. This one that's closer to the object is R1, and it's more curved, which means it's got a smaller radius. Okay. And now those both are positive because they're in our positive region. And so just focusing on this part, knowing that this is always positive, we end up with 1 over R1 minus 1 over R2, and those are positive. Yet R2 is greater than R1. And so if R1 is less than R2, then 1 over R1, the whole fraction, is a big number, and 1 over R2, R2 being bigger than R1, must be a smaller number, and big minus small is greater than 0. So it holds true, but now we can actually calculate what the focal length for this lens is. Okay. Let's go and try a diverging lens. What if we do this one? What if we go, this is also called a meniscus lens. This is actually the style what my glasses are. So we've got a shallow front and then a deeper back. So my eyeball would be over here. This is the shape of my glasses. Here's my object. So this is the positive area. Here's the negative area because the light's hitting that lens and really going this way. Alright, so with that being true, this is thicker on the edges than it is in the middle, so this should be a negative focal point, or negative focal length lens. So let's do our math here, again just focusing on this. Our radius of curvature, this one's tighter. I'm sorry, I didn't need to put an arrow there. This is tighter because it's more curved. So that's R2, it's the second surface, and R1 is the shallower curve, which means it has a longer radius. So now we have R1 is bigger than R2. So if I do my thing, 1 over R1, they're both positive, They're both positive because they're both in the positive region. 1 over R1 minus 1 over R2. Now, if R1 is bigger than R2, then 1 over R1 is small, and 1 over R2 is big, and small minus big is less than 0, so that is negative. So this lens would give us a negative value, as we suspected, because of our qualitative condition of being thinner in the middle than at the ends.